Okay, hang on. Aiden? Hello? Yo, was this your working or was it after? Okay, so you're not sure how to do this? Okay, so the key phrase is this base unit. What's base unit? Do you understand the base units? Okay, so these are your base units. So of all the units inside here, right? Of all the units inside here, the newtons is not the base unit. Do you understand that? So newtons is not the base unit. So what you need to do is you need to convert newtons into one of these base units. So how do we know what to convert the newtons into? We have to think of a formula. So newtons is for what? What's the units of newtons for? Give me an equation for force. Think of an equation for force for me. Hayden? F equals to ma. Okay. What is mass? Mass is kg. Acceleration is ms minus 2. Which also means that newtons in base units is kg ms minus 2. So what we do is we take this, we put it inside here, and then we multiply them together. Okay? Yeah, I mean that's how this is done. That's why your working looks like this. Kg meters per second squared, then the m squared times kg squared, and then you reduce it down, and I'm not too sure which option is it. Which one is it? B lah, right? Yes. Okay. 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 Let's look at the next one. Enzo, you send this one. Is that right? Okay. What's the question that you have? Where does area come into play? Mm-hmm. It um is the formula for energy over time, no lah. Uh-huh. Come on, think about this. So I think sometimes it's good if you can visualize it. This is a solar panel. The solar panel can produce 1000 watts, right? And if you remember back from the beginning, right? 1000 watts. How do you when you read 1000 watts, what should you read? 1000 joules per second. That means in 1 second, this solar panel, upon receiving sunlight, can give us 1000 joules every second. Okay? Okay. So the question is asking you for what's the efficiency, right? Efficiency. Okay? They tell you that in 1 second, each square meter of solar panel gets 800 joules of solar energy. So this is a 7.2 meter square solar panel. So how much joules of sunlight does it get? And go on, tell me the answer. 5760 joules. So in 1 second, the solar panel receives 5760 joules, but in that same 1 second, the solar panel can only produce 1000 joules of electricity. So what's the efficiency? I don't know. I don't want to care about the answer. You just tell me how to calculate the efficiency. 1000 over 5760. Yeah, I was waiting for you to say that. Okay? So 1000 over 5760, and how much would that be? Okay. All right then. Okay, Gordon, you've got a couple of questions that you want me to cover. Let me just cover those questions as well. Hang on. I think the first one you want me to do is this one. Can I ask you where the question is from? Okay. And this was which year? Last year only, huh? Okay. All right. So what's the key phrase in this question? I mean, yeah, I see you're working, I see your corrections and all those kind of things, but what's the key phrase in this question? Mm. The key phrase is constant speed. You write F equals to ma. Why would you go and take A as 1.5? Is it because it's convenient? It's not about how it's not about like you trying to force an answer out, you know. It's like you went to take the A here. They tell you it's constant speed. You went to take the A and you go and put it as 1.5. Then you came out answer and then you decided that okay, that's the answer. You understand what I'm saying? That's why it's wrong because you are doing things out of convenience. All right. So don't do that. If you know that's not supposed to be the case, then at least don't write it. I'd rather you not write this at all, and then just declare that you don't know how to do. But the fact that you tried to, like, don't tell me that you're at least you're trying, right? But you're doing it completely wrong because it's 1.5 meters per second. It's like it's not even acceleration. So you shouldn't even do it like that. You get what I'm saying? So tell yourself, all right, never ever try to force the velocity to be acceleration, especially if acceleration is like something else. Okay? And the trick to understanding this question is this thing here. If you take your paper, can you highlight constant speed? Constant speed means what? What's the acceleration? Acceleration is 0. Enzo, acceleration 0. What do you say? Yeah, that's what you should be saying as well, Gordon. Okay? The moment you know acceleration is 0, the resultant force is 0. So when you look at the object here, inside here, if you look at the object on its own, right, and you ask yourself, what are the forces acting on it? You drew it correctly, all right, but the numbers are completely wrong. This is 50 newtons, right? This is another red flag for me. You drew an arrow and it showed 5 kg. Do you understand why is it wrong? But why is it wrong to write an arrow and then write 5 kg there? I mean, apart from the fact that it's 50 newtons. Because 5 kg is mass. Mass is not a force. Drawing an arrow and showing 5 kg is a classic case of like not knowing the difference between mass and weight. Okay? Alright. It's not me trying to like point out like that you are incompetent or anything like that. I'm just saying that if you see your friend doing this, right, you better tell them not to do it. Because then they will start thinking that 5 kg acts on the object. That's wrong. It's right. It's 50 newtons. You get what I'm saying? Okay. So then I ask you this, okay? So I ask you this. Looking at this mass, right, that's hanging inside this lift here, looking at this mass here like this, right? What should the upwards force be in order for the F net to be zero? Like because like what Enzo said just now, F net is zero. So what should the tension be so that your resultant force is zero? There you go. Yeah. Okay. So I want you to see that they intentionally set a trap for you, right? Because they like one of the teachers who set this paper intentionally put this as an option, knowing that there will be some students that will put MA and put 5 times this 1.5 and then they will get 7.5 and then they're like, I'm waiting to see who will put this 7.5, right? And true enough, right? So you got to understand that there are options. There are some for MCQ, right? There are options, right, where teachers set options for convenience, right? Because they want to see who are the ones who always go for the most convenient answer. The one that oh, I don't understand what's this, so I'll just find the most uh the thing that connects the dots for me, and then I just plug it in and then see this. Do you know what will happen if your tension in the rope here is 7.5 only? If you draw it out, and I want you to see this, right? Can you look at this object? I'm not talking about the entire leaf. I'm talking about this object here, right? Look at the forces acting on this object. Can you tell me what's going to happen to this guy? Not the word I'm looking for. Not the word move. Move is not the word I'm looking for. Yeah, it will accelerate downwards. Why would it accelerate downwards? The resultant force is pointing downwards, right? Okay. So be very, very aware of this, right? Do not fall into their trap, right? If the teacher was kind enough, the teacher wouldn't have put this as an option, right? Then maybe if you get 7.5, you realize that, that's not one of the options, something must be wrong. But like the thing is this teacher set the trap here like this. So don't fall into that trap. Okay? Right? If it accelerates downwards, it wouldn't be moving at constant speed. Right? So the crux of this entire question here is zoom in onto this word constant speed. In fact, right, all these dynamics questions, right, the number one thing to watch out for is the word constant speed. Every time you say constant speed, oh, constant speed like this, then you should be very quickly understand that resultant force is zero, which means that the forces must act in such a way so that the resultant force is zero, right? And the only way to do that is the tension is zero. But you know what? I'm going to have to ask you all to do extra things here, right? So Gordon, right? This is on you. You have to help me answer this, huh? Okay. Same mass, 50 newtons weight. Okay, same mass with a 50 Newton weight. Okay, right. I'm going to tell you that now the lift is going to accelerate upwards at 2 meters per second squared. I tell you that the acceleration is 2 meters per second squared. Can you tell me what's the tension in this cable now? I want you to find the tension in the cable. Right, how much would the tension be? Would it be 50? Would it be slightly less or slightly more, or what is it then? Like, how much would the tension be? Hmm? Hidden what? Sorry, what do you say? 60 newtons. All right, we'll see. All right, Gordon, still finding? Okay. Okay, guys, 150. Wow. Okay, hang on. Okay, guys, I'm more concerned about the process rather than the answer. So I want to show you the working, and it's the working that you need to pay attention to. Very, very important. Okay, if something accelerates upwards, means that resultant force is pointing where, Gordon? Upwards as well, right? Does it mean that T is bigger than the weight, mg? It is, right? So then you have to understand that we have to write it like that. T minus 50 is equals to the resultant force, which means that it's equals to F net, which means that it's equals to MA. So T minus 50 equals to MA, but here's the thing, the M is 5, not 50A. You get what I'm saying? And therefore the A is, and there, sorry, and therefore this one is 2 here. And therefore the T is equals to 60 newtons. Okay? So when you say 150, I believe you thought that the M was 50. You get what I'm saying? No, but here's the thing. That's where your common mistake is. You understand the you understand the concept. You understand how to work the equation, but you kept mixing up M and weight, mass and weight. You kept mixing up that, right? That's why I'm saying, right, it's very dangerous, right? Whenever I see working like this, right, this is a red flag to me, because then you sort of like, I think you're not very clear. So mass is not a force. 50 newtons is the weight, is a force. 5 kg is a mass, right? So when you see M, you use 5. When you see mg, then you use 50. Understand? Okay, cool. All right. Let me get back to your other two questions later on. Let me just finish up Aiden's one. Aiden has one question here. Eh? It disappeared, Aiden? You figured it out? Okay, right. Don't need to delete lah, but okay. Okay. Let's do this one. This one here. Let me just find some space. Okay, let's do 16. A ball is thrown vertically downwards. All right, vertically downwards. Right, with a velocity of 30 meters per second from a height of 240 meters. Air resistance is negligible. G field is 10. Right? What is the velocity of the ball just before it reaches the ground? Okay, just before it reaches the ground. Okay, so I can see that you did try to do the GPE equation, right? Sorry, the energy method. But I must tell you that am I missing? Are you missing a square there, or it's just that you cropped without the square, Gordon? There was a square, right? So you crop the picture without a square, lah, right? It's fine. Okay, but this method is not right. Okay, I'll explain why in just a while. But I want to explore using this idea. Why don't we try using kinematics first, right? There's two ways, kinematics or energy, right? I want you to see this, kinematics, Okay, if you do kinematics, velocity time graph, why am I inclined? Why am I like suggesting to use kinematics? Because they have initial speed, they have distance, and they ask you for final speed. So it's kind of like initial speed, distance, final speed. It might feel like a bit of kinematics. If you were to draw the graph, it starts from 30, it accelerates downwards, okay, and then it accelerates downwards, and then it hit the ground, right, at a certain time t. We don't know what t is. In fact, we don't even know what this final value up here is. All right, but we do know that this area here is 240. 240, yeah? Okay. I'll show you the speed here, right? The v here. So v equals to u plus at. Okay, u plus at. U is 30. So this one you didn't drop from rest. This one you throw downward. So the initial speed is 30. So u is 30. 30 plus 10t. So you literally can write 30 plus 10t, right? And then you can, yeah, right? So the trick here is that you actually can solve for t. Then after that, sub in t into this one here to find the final velocity. You can do that. So it's a bit of math. It's a bit of graph work. So let's try this first, okay? All right. Do you see the area of the trapezium here, Gordon? Can you read out the equation for this area? So the area is equal to what? For trapezium, yes. Half times. Uh-huh. Okay, so what is u in this case? Uh-huh. Okay, good. Mm-hmm. T, right? So the area is 240, right? So basically 240 equals to half times 60 plus 10t times t, right? This is going to be a problem, right? Do you foresee that this is going to be a problem? Why? basically quadratic, right? Correct or not? Then you have like two answers, right? Okay, is it that big a problem to you at this time? Can you find t? Do you have a quadratic solver on your calculator? You have, right? So technically you can solve this, all right? You can solve this. But obviously, like some students will be stuck here. So and then they're like, oh, is this the correct way? I'm gonna tell you this, okay? You will start doing this for E-math later. I think either E-math or A-math, right? In Sec 3, Sec 4. I think in Sec 4 lah. Sec 4, I think one of the maths, either E-math or A-math, has kinematics, right? So you'll be exposed to kinematics again then, right? And you will get this kind of question. So you have to learn, right, that you have to just understand, right? We just have to accept that T have to be calculated using quadratic. This is if you use the kinematics method. Now, if you don't want to use the kinematics method, you can use the energy method. Okay, the energy method. Do you understand the energy method? Which is what I see you were trying to do, right? But that's not quite the right way. So I'm going to show you how to use the energy method, okay? All right. So at the start, did the ball have KE? Okay. So we're going to write half mu squared. Then as it falls down, it's going to lose GPE, right? And then therefore at the end, right, it's going to get a final KE just before it hits the ground, half mv squared. You understand this? Okay, so whatever you do, you have to remember to take half mv squared minus half mu squared equals to GPE. Okay, or you know what? Or maybe this is not intuitive to you. Maybe we do it this way instead. We take the initial KE, half mu squared, plus the GPE that you convert into KE, and this is equals to the final KE. Would that be more intuitive for you? Up to you. No, it's fine. I mean, I just simply rearranged it. Yeah, you get what I'm saying? Right? I think in this way, right? Anyway, in this way, right, I can make V the subject anyway. Right? Yeah. So one big thing that you realize is that if you want to use the energy method, always check. Did they give you mass? Because I got a mass term here. Did they give you the mass? They didn't, right? Oh no, then how? But it's okay, right? Because every one of the terms here have a m inside. So it cancels off. Are you working on it? Huh? Yes, you are? Okay, good. So which means that this is, so you end up with half of 30 squared plus 10 times 240 is equal to half of v squared. Then you find v. You basically have to square root something lah. Can you work it out for me now? Because I got another thing to point out to you. (75.5 meters per second). Is it? All right, so D is your closest answer. It should be 76 lah, the answer key. All right. Okay. Right here, right now, I want all three of you to remember this. I've said this a couple of times before in class, and I again want to remind you. Okay. So sometimes, let me just okay, sometimes a very, very common mistake some students do is this, right? So can I just ask you to pay like extra attention to this? Okay. So some students, what they do is this: they take the MGH and they equal it to the half MV squared, right? Because they think, oh, GPE convert to KE. Okay. right? Then, okay, m cancels off, that's fine. So some students will do this, 10 times 240, then equals to half v squared. Can you find out what v is for me? If you do it this method, can you punch in the calculator for me, Gordon? 70 meters per second. Am I right? Okay. So the problem is some students what they do is, oh, if I take the GPE and I convert it to KE, the speed that I gain is 70. Then some of them might take 70 plus 30 and then say that, oh, the ball will strike the ground at 100. Okay? Right here, right now, I want to point out to you that this is absolutely the wrong way of doing it. Okay? Because by doing so, right, you're adding the velocity. Right? You cannot add the velocity. You must add the energy. Right? Anyway, the option didn't even give you 100, right? Yeah. The teacher didn't set the trap. Right? I tell you, if the teacher put in like one of the options as 100, right? Confirm guarantee the student, one of the students will put in, right, 100 meters per second as the answer, right? So just be aware, right, not to do it like this. But I think you might not have thought of this because like you know, none of the options was here. So yeah. Please, again, one more time, remember, okay, you see, I see your corrections here also. It says, right, EP loss equals EK gain. Correct, that is correct. That is great. This is correct, okay? But usually answer keys don't show it, and therefore answer keys are not always the most complete, which annoys me the hell, right? So always remember, right? Especially when you start off with initial KE. This is a common trap that teachers love to use. So the change in GPE is equals to the change in KE, right? One more time, right? So the MGH, right? Whatever the GPE loss is equals to half mv squared minus half mu squared, right? It must always be written out. Energy, right? Final energy minus initial energy equals to this, right? Do not convert energy, then you take the velocity and add it back into the velocity on top, right? Never ever do that. Can I get a okay from all three of you? Okay, all right. So always remember, right? You find the difference in the energy, then you find the velocity. Don't go and find the velocity and then go and add the velocity. Okay, last question from Gordon. Hang on. All right, let's look at this one here. All right, a hard stone hits the ground vertically. Hang on, where's my A hard stone hits the ground vertically, and comes to rest almost immediately, right? As the stone hits the ground, what's the direction and size of the force acting on the ground? Oh, okay, this is a hard question. This question here is hard, man. Oh gosh, this question sucks. Okay. Why would a hard stone hit the ground and come to rest immediately? Like what's up with that? Like how come it didn't bounce? Okay, hey, before that, right? Okay, so the question is, why doesn't it bounce? Right? So there's a difference, right? If you drop a basketball on the floor, it'll bounce. Okay. So now we are dropping a hard stone on the floor. Like, why doesn't it bounce? Right? And the reason why it doesn't bounce, right, is a very silly reason, right? Because the ground is soft. It's like maybe you're dropping it on grass. I mean, if you realize that if you try to bounce a basketball on grass, also it won't bounce very much. You get what I'm saying? Right? If you did drop a rock on a hard floor, it probably might bounce. It might bounce a little bit, right? You know, maybe because hard stones are not built for bouncing, right? The key thing here is that it comes to rest almost immediately. Means that the floor is a bit soft. Maybe you're dropping the hard stone into mud. I will talk about the basketball on the floor in just a while, right? I'll talk about that in just a while. But for now, right, I'm gonna drop this rock onto this soft surface, right? Okay. So, Gordon, I think, or maybe I switch someone. Enzo, your turn, Enzo. Okay, all right. Can you tell me what happens to this rock as it falls? Like, what happens to the rock as it falls? Okay, there's a weight acting on it, right? And then it gets what? What's the deal with it? How about its speed? Okay, so I'm asking you about the speed. So let's say we don't care about terminal velocity or anything like that. Like basically the rock will get faster and faster and faster, right? Okay, so just before it hit the ground, just before. So you see, I'm dropping the rock, right? I'm dropping the rock and letting it hit the ground, right? This is not the same as letting the rock sit on the ground. Like, if the rock is sitting on the ground, okay, for this, right, Enzo, if the rock is sitting on the ground, what are the forces acting on the rock? Weight and normal, mg and normal contact force, right? Well, are they both equal magnitude? They are, right? Okay, so if you let the rock sit on the ground, right, the normal contact force is actually equals to the mg. That means you don't drop it. But if you do drop it, it's a different scenario, right? If you do drop it, let's say you have a rock here like this, and then you drop it, drop it, drop it, drop it, drop it. Okay, so the instant just before it hit the ground, right? So just before it hit the ground, what's the speed of this rock? Yeah, basically is the whatever speed that it has just before it hit the rock, right? Okay, then I hit the ground. So then it hit the ground. Now this rock hit the ground. So I'm just going to draw two overlapping pictures to show you that the rock hit the ground. And what is the final speed? Okay, so the final speed is 0. So just before it hit the ground, I give it the symbol U, and then now it hits the ground already. The final speed is 0. So let me just kind of like shade this a bit lighter a bit. Let me see. Okay, right. This is like the the just before it hits, the very faint picture just before it hits, and then the solid one is just after it hits. Okay, all right. So during this time this thing okay. So you see right, the very faint one so we have to imagine everything in slow motion now, like right. So imagine that very instant when the rock just starting to touch the floor until it completely comes to rest in the floor. Okay, all right. You tell me that this is u maximum speed and this is 0. All right. So where's the acceleration of the rock during this time? Where's the acceleration of the rock? Acceleration. That's why I say this question is not easy. No, the acceleration is upwards, A. Yeah. I'm asking you, where's the acceleration pointing during this coming to rest period? The acceleration is pointing upwards. It's basically decelerating. Does it make sense that it's decelerating? I mean, maximum speed becomes 0 is decelerating lah. But the acceleration is pointing upwards lah. Gordon, can you understand this? Aiden? Okay Alright, so back to Enzo Okay, Enzo, in order for the acceleration to point upwards, okay, what should the forces be like acting on the rock during this contact period? So it's uh-huh. There you go. All right. So the N force must be bigger than the mg. But this is only during this period of time when it's trying to slow down, because the rock needs to slow down. And in order for it to slow down, right, the floor needs to give it a very large impact force, right? This is the normal contact force, right? A very big impact force to help it slow down to 0. So upwards force is bigger than downwards force, resultant force is pointing up, acceleration is pointing up, the rock decelerates and it comes to rest. After it has come to rest, it will look like this. After it's come to rest already, the N force will be equal to the mg. Gordon, do you understand this? Okay, all right. So this force, okay, wait, hang on, Gordon, I need to check in with you. Gordon, how do you read this thing here? Read this in English, like, give me a phrase for this force. What force is this? By the ground on the rock. By the ground on the rock, right? Yeah, okay, good. All right. So this is the normal contact force by the ground on the rock. But what is the question asking for? The force acting on the ground by the rock, right? which happens to be N prime. I made you read out that force. You said that it's normal contact force by ground on rock, right? Because I wanted you to see that there is an N prime, action reaction pair, Newton's third law, that there's a force on ground by rock, which is the answer to this question. So N prime is the action reaction pair of N. N is bigger than mg as it's slowing down, right? So you look for the option that says this one. So what is the direction of size of force acting on the ground? It will be downwards and larger than the weight of the stone, right? B should be your answer. But this is only during the deceleration portion, which is why, right, they're asking as it hits the ground. That means they're asking about the deceleration part, not after. Because I can change the question and say that after it has hit the ground, what's the force acting on the ground? It will be the normal contact force, which is equals to the weight. Okay. Hello. Enzo, Gordon. Can okay. So yeah, basically this question here, right, is difficult because they're asking you for that very instant, right, when the rock is coming to rest right here. Okay, that's why the normal contact force is bigger. Now I said I'll do the basketball, so I'll do a quick one. All right, so it's the same thing. So a basketball bounces, right? A basketball bounces, right? The ball hits the ground and then it bounces up, right? Okay. So now the question would be, how is this different from the previous case? Actually, it's exactly the same. In fact, right, this one here is the ball hitting a hard surface, and in fact, the normal contact force, let's say this is weight, right? The normal contact force of this will be a lot bigger. Like the normal contact force for this will be a lot bigger, right? This is at the point of impact. Why is the normal contact force so big, right? Because not only you make the ball like basically when the ball bounces, right? You see the ball's velocity, right? The ball's velocity, it needs to change direction. It needs to go from going down to going up, right? How do you change direction? You go down, you stop, then you accelerate upwards. So this normal contact force must be like a lot bigger actually, right? Because the normal contact force would mean that it can help the ball come to a stop at the bottom and then help the ball accelerate upwards again, right? So it's the same thing, except I would think that for a bounce, the normal contact force is even bigger, right? So if you were to draw this thing here, right, the acceleration, right, is upwards like this. So for a ball bouncing, there's two things happening: is decelerating, and then it's accelerating, right? It's decelerating as it's going down, as it's coming to a stop on the floor, and then it accelerates after the bounce. It accelerates upwards after the bounce. Okay. Basically, I'm done here. Are you guys gonna practice any more paper ones or anything? Jeez, you got chemistry paper tomorrow? That's crazy, man. Okay, okay. All right. Then logging off now. Oh, I mean paper one. Then you can do a bit of physics papers also. What? Yeah. Okay. 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 All right. If there's anything else, then if there's nothing else, then okay. See you guys. Let me know when you get your paper back. Okay, and then let me know if I can do a paper review. Yeah. Yeah, and yeah, and you guys are not going to be learning new topics, so I won't see you for the rest of the year, right? Except for the paper read. Ah, shit, what? Oh yeah. You're supposed to join in after when I'm teaching waves for the MGS. Okay, I'll let you know. It's probably going to be one lesson only, so we'll just find one day for you to come in, one of the Saturdays lah. Okay. All right. Thanks, guys. Bye bye.